Hello, welcome to the second day of Chapter 6. Today we're going to learn about probability models. Now the big idea in probability is that chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. Now casinos and many other businesses make a fortune off of this idea. The fact that in the short term, the person who's playing the casino game, they can win a little bit. Um, but in the long term, the casinos have the advantage. Empirical, whenever we say that the data or this probability is empirical, it means that it's based off of an observation rather than a theory. So say like a batting average is empirical data. It's something that we have observed and we use that data to predict the future. Randomness and probability. We call a phenomenon random if an individual outcomes are uncertain, but there are nonetheless a regular distribution of outcomes in a large number of repetitions. The probability of any outcome of a random phenomena is the proportion of times that outcome would occur in a very long series of repetitions. That is, the probability of long-term relative frequency. Now, keep in mind that it's long series of repetitions, long-term relative frequency. So we can get a probability like we did in the simulations by simulating it 10, 20 times, but those probabilities aren't as good as if we would have done 100 simulations or 1,000 simulations. So keep in mind the more repetitions, the better the probability is. Here are some more terms. A sample space, it's denoted with a capital S, of a random phenomena is the set of all possible outcomes. An event is any outcome or set of outcomes of random phenomena. That is, an event is a subset of a sample space. And a probability model is a mathematical description of a random phenomenon consisting of two parts. There's a sample space and a way of assigning probabilities to events. All right, when you roll two dice, this right here is a sample space. It's really important for you to understand that there is 36 possibilities, and getting a 2 on one dice and a 1 on the other, and a 1 on one die and a 2 on the other, those are two different possibilities. So there's 36 possibilities, and this is something that you really have to know. Now, if we want to, so this is the sample space. An event is like roll a 5. The event that you roll a 5, there's 1, 2, 3, 4 different ways we can roll a 5. And we can see that the sums are on diagonals. So rolling a 5 is those 4 numbers. So what is the sample space if we add the sum of the dice? Well, the sample space can be 2, 3, we can get a 4, a 5, a 6, 7, 8, 9, 10, 11, and 12. Now, each one doesn't have an equal probability of occurring, but these are all of the possibilities that we can get by rolling two dice. What's the probability that the sum of the two dice is 11? Well, let's look back at our sample space. 11 would be here and here. So the probability will be 2 out of 36 different options, and this will reduce to 1 over 18. Now, if we flip a coin and roll a die, what is the sample space? So we could get heads and then get a 1. We could get heads and then roll a 2. Heads 3, heads 4, heads 5, heads 6. And then we could also get tails. Tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Now this is all the possible solutions we can get from doing those two random events. Now, if I wanted a tree diagram to represent that situation, that is underneath here, I could either get a head or a tail initially, and then from that I can either get 1 through 6, 1 through 6 from each of those. So you can see heads 1 through 6 and tails 1 through 6. The probability of each outcome is equal. So each of these is equally probable. So it would be 1 out of, looks like there's 12. So 1 out of 12 for each of these. The multiplication principle. If you can do a task n sub 1 numbers of ways, and you can do a second task n sub 2 number of ways, then both tasks can be done in n sub 1 times n sub 2 number of ways. An example of that is if you go on vacation and take 3 pairs of pants and 5 shirts, how many different ways can you wear them? Well, you can take 3 times 5 to get 15. Now, another way you could think about this in a more complicated way, or I don't know what complicated, but maybe more visual. You can take pant 1, pant 2, and pant 3, and there's 5 different shirts that you could get with each of these. So shirt 1, shirt 2, shirt 3, shirt 4, and shirt 5. So there's 5 possibilities for this one. There's shirt 1, shirt 2, shirt 3, shirt 4, shirt 5. I'll just do 3, 4, 5. And then there's 1, 2, 3, 4, and 5 from, oop, I can't even write a 5. All right, there we go. So there's 5, 10, 15 different ways, and this is a more visual way to see it, and this is just a shortcut. All right, now sampling with replacement and sampling without replacement. You really have to be careful when you see the word replacement and pay attention to whether it's with replacement or without replacement. For example, in a bag, if there are 30 marbles, 15 are blue, 5 are red, and 10 are green, what's the probability of drawing 2 green balls without replacement? Maybe it'll even help you in the test to underline that word without replacement, so you keep in mind that we're not putting the marbles back in. Well, the first green ball that I take out, I have a 10 out of 30 chance of getting a green ball. But my second green ball, there's only 9 marbles that are green left in the bag out of 29. So now we just multiply these values to get 90 out of, actually, I'm going to take a step back. I don't have a calculator with me right now, so it's a little bit easier if I would just reduce this ahead of time. 10 over 30 is the same thing as 1/3. And so 1 times 9 is 9. 29 times 3 is, I think it's 87. I should probably do my math just so I don't look like a fool. And it is 87. Wonderful. All right, so that was without replacement. If we do it with replacement, the probability of getting a green on the first time is 10 out of 30 again. And I put the green ball back in, so I still have a 10 out of 30 chance of getting a green ball in the second one. So if I multiply these, this is like 1/3 times 1/3, which is 1 times 1, which is 1, over 3 times 3, which is 9. So I have a 1 in 9 chance of getting 2 green balls if I draw it with the replacement. All right, now here are some rules in probability. There's some pretty basic rules to start out with, and then they get a little bit more complicated. The first rule, the probability of A, or the probability of any event A, has to be between 0 and 1. If it's 1, it means that that is definitely going to occur. If it's 0, it means it will never occur. Rule number 2, if S is the sample space of that probability model, the probability of the entire sample space is going to equal 1. So if we add up all the probabilities in a sample space, it always has to equal 1. Rule number 3, 2 events A and B are disjoint, pretty important word, And they're also called mutually exclusive, just another way of saying the same thing, if they have no outcomes in common, so can never occur simultaneously. If A and B are disjoint, there is a rule that we can use uh, that says the probability of A plus the probability of B is going to be the probability of A or B. This is the addition rule for disjoint sets. Now, disjoint, think in a Venn diagram, they're things that have no overlap. So it means there's nothing in common in these two sets. So if this probability is 0.2 and this probability is 0.1, the probability of, say, A or B occurring would be 0.2 plus 0.1, which is 0.3. I should say this is the probability of A or B. Now, there's another way we write this. We can say that this is the probability of A union B, and we're going to get into that more in later lessons, but just a different way to write probability of A or B. Now, the complement of an event A is the event that A does not occur. So you can find the probability of drawing a black card, and then the probability of black card complement would be the probability you don't draw a black card. And to get the complement, you just take 1 minus the probability of whatever event you have. Now these last two are a little confusing, so I have another slide to explain them. The complement is a little easier. Say if I'm going to roll one die, the probability of getting a 6 is 1/6. Now the probability of not getting a 6, so we're not rolling a 6. Well, there's 5 choices out of 6, so it's 5 out of 6. Notice that this is the same thing as 1 minus 1/6. So we could have just taken 1 minus 1/6 to get that answer. Now, disjoint events, also called mutually exclusive, are two things that can never have overlapping events that don't have any overlapping pieces. For instance, drawing a red card and drawing a black face card. There's no way you can draw something that's a red card and a black face card, so that we call them disjoint events. There's a rule with disjoint events is if we want the probability of A or B, we can just add up the two probabilities. So if we have the probability of A, that's drawing a red card, that's 1/2. The probability of drawing a black face card, well, there's 6 black face cards out of 52 cards in a deck, and that reduces to 3/26. Now I can find that probability of getting one or the other by adding those two together. 1/2 is 13/26, and when I add them straight across, I get 16/26, which can reduce a little bit further to 8/13. So there's an 8/13 chance that you'll either draw a red card or a black face card. All right, if 2 dice are rolled, what's the probability that the sum of the dice is either 3 or 8? Well, let's first find the probability that you get a 3. You can get a 1/2 or a 2/1, so that's going to be 2 out of 36. Now let's find the probability that you roll an 8. You could get a 1 and or a 5 and a 3, a 6 and a 2, a 4 and a 4, 5 and a 2, and then another 6 and a 2. So that means that there are 5 different ways out of 36. Now there's no way you can get a 3 and an 8, so these have to be disjoint events. So the probability of getting 3 or 8 is going to be 2/36 plus 5/36, which is 7/36. All right, we're going to draw Venn diagrams to show these new ideas about union, intersection, and complement, and mutually exclusive. Union, if I have two events, union means, say if this is A and this is B, A union B, that U stands for union, is everything in A along with everything in B. So here I've shaded in what A union B represents. The intersection is if I have the intersection of A and B, it's what's in both of these. So this section right here, A, and this is like an upside down U, that's called intersection. Now, this is also called A and B, and this is A or B. And or make a big difference in a word problem. So you can read a whole word problem, and whenever you see an and and an or, you really have to pay attention to what the question is asking, because ands are usually talking about an intersection, and ors are usually talking about a union. All right, the next one is a complement. So if that's A, call this event A, the complement is everything that's outside of that event. And we'll call that a complement. Mutually exclusive or disjoint events are just two events that don't have anything shared. See how here A and B have something shared? Same here. Here there's nothing that's shared between the two events. All right. A large shopping store gave details on how their customers will pay for their items. The rest of the people will use cash. What is the probability that they use cash? Well, let's see what these probabilities add up to. These two add up to 0.42. These two add up to 0.33. So that's 0.75 together. So if 75% of the people use some sort of credit card, the people that use cash are going to have a probability of 0.25. So what is the probability that you use a Visa or MasterCard? That's just right here. Now these are mutually exclusive or disjoint events, so we can just add those together. 0.3 plus 0.12 is 0.42. Now in this Venn diagram, we have these two events. The first event is the first toss of a coin is a head. The second event is the second toss of a coin is a head. So describe what each part of this Venn diagram describes. Well, in the middle, this is where the first time you get a head and the second time you also get a head. So we'll just call that HH. This dark green over here is when you get a head the first time, but notice how it's not in B, so you do not get a head on the second time, so you'd get a tail. This section over here in B, you get a tails the first time, but you'll get a head the second time. And now outside of these two circles, you're not going to get a head either time, so that's tails, tails. So to find the probabilities of each situation, each one has a 1/4 probability because each one is equally likely. There's a 1 out of 4 chance of getting each of those. All right, here's the homework. Good luck.